Hello everyone. The title of this video is Solve Exponential Equations. Each exercise that I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. It is their Intermediate Algebra 2nd edition text. I'm in section 10.2 titled Evaluate and Graph Exponential Functions, and I'm working under the heading Solve Exponential Equations. I'm only going to be working on the even numbered exercises, the ones that do not have a link to a solution, right, like the odd numbered ones do. So I'm going to be working on 96, 98, 100, all the way down to just 108. I will also have timestamps for each of these examples in the description of the video below. So you'll see example 1's timestamp is where exercise 96 begins, example 2 for 98, example 3 for 100, and so on. I also request that when I start a new question, pause the video and try to work on it yourself first before watching me do it and comparing. Because if you're just watching me do these things and not practicing on your own, chances are you're not learning all that much. Alright, so in each of these exercises, we're just simply asked to solve the equation. Alright, find the values I can replace the variable with to make a true statement. And I'm starting with example 1, exercise 96. And I have this written out here. Example 1, number 96 from the text. Alright, so these are exponential equations because the variable we're trying to solve for is in an exponent, right? It's in a power. So you see here on the left side I have a base of 2 raised to an exponent of 2x minus 3 equals, and then on the other side we have 32. Alright, so before I get into actually solving this, I want to talk about the graphs of exponential functions real quick. And you've seen me talk about these in a previous video on graphing exponential functions. I just want to really recap it here. The graphs of basic exponential functions. So if you have y equals, or f of x equals, some number, some positive number, b, to the, just the x power. Remember how these looked. Right, so again, b is some positive number here. Right. Remember, if b, right, if the base was bigger than 1, then the graph, looked like this. Just doing a rough sketch here. It was an increasing function. Shoots up very rapidly as you go to the right. But as you go to the left, right, the x-axis was a horizontal asymptote, right? The graph approaches the x-axis but never actually touch it. Right. And the other case we saw was if the base was between 0 and 1, so like a half or a third or something, the graph of that kind of an exponential function, y equals b to the x, was a decreasing function. Right, something like this. I just kind of flip the first case over the y-axis. So again, all positive outputs, right? The x-axis was again a horizontal asymptote and all that. But in either case, right, exponential functions are what they call one-to-one. They're called one-to-one, meaning that, again, let me label these x and y axes here. That just means, sure, it's first of all, it's a function. So every x value in the domain, goes to exactly one y value in the range. But also, being one-to-one means that the other way around is true. That every y value in the range, right, and the range is, positive numbers for these y equals b to the x functions. Say, this value is in the range here, right, this y value, and it corresponds to exactly one x value. Right, let me call this y star and x star. But that's going to be the case for any y value, any value in the range. It goes to exactly one value in the domain and no more. So another way to say this is that if, say, b to the m power were equal to b to the n power, well, the only way this is going to happen, two expressions with the same base being equal, this is only going to happen if those powers are the same number. Right? You see from the graphs here, you can't have two inputs going to the same output in an exponential function. So I can't have two powers of b that are the same if those powers are different. Right? These powers then must be the same. Right? And this is called the one-to-one property for exponential functions. Right? So if b to the mth equals b to the nth, then m must be the same as n. Right? Those exponents must be the same. And I'll put this in a box. I'm going to be using this for the entirety of the video. This one-to-one property. Right? The one-to-one property for exponential functions. Alright, so that's going to be key. Alright, so first I want to get all these equations I'm trying to solve in this form, in the hypothesis of the one-to-one property. I want both sides to be expressed as an exponential statement with the same base. Right, so that's going to be the first step. I'm going to get both sides in the same base. Right, so the left side has a base of 2, right, and an exponent of 2x minus 3. The right side, is 32 to the first power at the moment, so this has a base of 32 and an exponent of 1. So these right now have different bases, but hopefully you recognize 32 as a power of 2. So I rewrite, the left side I'll keep as base 2, right, 2 to the 2x minus 3 power. The right side, let me separate this stuff here. The right side, 32, that's 2 to the 5th power. Right? You can check it, 2 times 2 times 2 times 2 times 2. Right? 2 to the 5th power is 32. Now I have an equation of the form of the hypothesis of the one-to-one property. Right? And because exponential functions are one-to-one, right, so what we're going to do here is we're going to apply the one-to-one property. The only way two expressions with the same base are equal is if their exponents are equal. So if 2 to the 2x minus 3 is equal to 2 to the 5th, that means that 2x minus 3 must be equal to 5. And then we solve, of course, right? Solve this resulting equation. And then, of course, check your solutions at the end. Now I would add 3 to get 8, then divide by 2, get x equals 4, and then don't forget to check, back in the original equation. Alright, so if x were 4, 2 times 4 is 8, 8 minus 3 is 5, 2 to the 5th power is 32. Right? So this is the solution to this equation. X equals 4. But don't forget to check, back in the original equation, as you always should, when you have equations. Okay, and I'm going to be following these same steps every time. All right, trying to get both sides written in the same base, and then after they're written with the same base to some power, and make sure it's a single base to that power. We'll see some problems later where there are multiple expressions with the same base. I want a single base to a power equals a single base to a power, and those bases are the same. And then we'll apply the fact that exponential functions are 1 to 1, and say, oh, then their exponents must be equal, right? And solve that resulting equation and check. All right, so again, in example 2, this is exercise 98 from the text. All right, so here we have 3 to the x squared power. Right, the exponent is the expression x squared equals 81. All right, now 81, both sides in the beginning don't have the same base. Right? This side has a base of 3, and this side has a base of 81. But I'm hoping you see that 81 is actually a nice power of 3. 81 is 3 to the 4th power. Right? So now I have what I want, right? Both sides as a single, the same base to an exponent. And the only way these are going to be equal, again, I'm applying this 1 to 1 property. The only way these are going to be equal is if their exponents are the same. Right? So if x squared is equal to 4. So there are two solutions here, right? Using the square root property, we see that x is either the square root of 4, which is 2, or x equals, the opposite of that, right? Negative 2 squared is also 4. And like I said in the beginning, don't forget to check. Right? Now, 2 squared is 4, positive 4, 3 to the 4 is 81. So, positive 2 works. And the same thing goes for negative 2. And when I plug it in, negative 2 squared is positive 4, and 3 to the 4 is 81. So both work. This one has two solutions, positive 2 and negative 2. Wonderful. All right, so next question. Same procedure, right? Trying to get both sides to be written in the same base, right? The same base to a power. So on the left side we have 4 to the x, right side we have 32 to the first, right? So this is base 4, base 32. Now you could try writing both sides in base 4. I mean, that's not wrong. It's just there's a simpler base that both can be written in. 4, right? 4 is a power of 2, right? 4 is 2 squared. And 32, as we saw in question 1, is 2 to the 5th. So I can write both of these bases with a base of 2 instead. But then you might have to, and then you're going to also have to apply some properties of exponents to help simplify here. So I'm replacing 4 with 2 squared. Now remember, whenever you replace something, whenever you substitute for an expression, use parentheses. So instead of 4 to the x, I'm replacing 4 with 2 squared. Now, I'm hoping you recall some properties of exponents. There was that power to a power rule. If I take a number, raise it to a power, say b to the m, and then take that number and raise it to another power, so b to the m and then that to the nth, you can keep that base, right, b, and the new exponent will be the product of these exponents, m times n. So I'm hoping that sounds familiar, the power to a power property. I'm going to be using that here. And then on the other side, as I said, 32 is 2 to the 5th, and there's really no need for parentheses here. This isn't being multiplied by anything or raised to any powers. And now I use that power to a power property, right? 2 squared to the x is 2 to the 2x power, right? 2 times x. And then on the right side I have 2 to the 5th, and now I can apply that 1-to-1 property. I'll do it over here. All right, now I can apply that 1-to-1 property. These both now have the same base to a power, and the only way this is going to happen is if the exponents are the same. So if 2x is equal to 5, or if x is 5 halves, right? 5 divided by 2, or 2.5 if you want to write it as a decimal, and check it. And I'll do this off to the side. Now you can do it by hand, you can do it with a calculator, whatever. Now 4 to the 5 halves power. Hopefully, I'm hoping you remember how to evaluate fractional powers. Remember, the denominator of 2 means you're taking the square root of 4 and then you raise it to the numerator power, right? That's the same thing as 4 to the 5 halves. And the square root of 4 is 2. 2 to the 5th is 32. So this totally works. Right? X equals 2.5 or 5 halves or 2.5 is the solution of this equation. Great. All right. Next question. So the left side has a base of 4. We have 4 to the x plus 3 power equals, and then 16 to the first. So base 4 on the left and a base of 16 on the right. But, you can probably remember, right, hopefully, that 16 is a nice power of 4. So I can write both sides in base 4 right now. Right, 16 is 4 to the second. Right. So the left side I'm not changing. I'm going to keep it with that base of 4. So 4 to the x plus 3 power. And the right side, 16 is, 4 squared. And no need for parentheses here. It's not being raised to any powers or multiplied by anything or added to anything. And now I can apply, since both sides are the same base to a power, I can apply that 1-to-1 property. The only way these are going to be equal is if their exponents are equal. Right? So if x plus 3 is equal to 2. And I just simply subtract 3 from both sides. We get x must be -1. And I'll check this out loud. If x were -1, go back to the original equation. Right? -1 plus 3 is 2. And then you have 4 to the second power is 16. That is totally true. Right? So this works. Fantastic. Alright, and you notice I'm doing the same thing for all of these. Alright, the next question, again, is going to involve your knowledge of certain properties of exponents. So I'm hoping that you recall this from a previous video as well. Remember that a number, a sum base to a negative power, so say b to the negative n, is just the reciprocal of the positive power, right? 1 over b to the positive n. All right, so here we have 3 raised to the x squared minus 2x power equals, and then over here we have a base of 1/3, right? This is 1/3 to the first. So they don't have the same base right now. But if you remember your negative exponents, remember that 3 to the negative 1 is 1 over 3 to the 1, right? Or 1/3. So I can rewrite 1/3 as an expression with a base of 3, right? 3 to the negative 1. So we have 3 to the x squared minus 2x power equals, and then 1/3 I'm rewriting as 3 to the negative 1. And now I can apply the 1-to-1 property. Right? Both sides are the same base to a power. And now I can apply this 1-to-1 property and say the only way these are going to be equal is if their exponents are equal. So if x squared minus 2x is equal to negative 1. Okay. This is a quadratic equation. Should be able to solve this, right, by completing this square, or if I add 1 I can use the quadratic formula. X squared minus 2x plus 1 equals 0. Taking this over here now. You can use the quadratic formula if you want, but this is nice and factorable. This actually factors to x minus 1 squared. It's x minus 1 times x minus 1. So we have x minus 1 squared equals 0, and the only way this is happening is if x minus 1 equals 0. Right? The only number that you can square and get 0 is 0. So x must be equal to 1. And now we check it. Right? Don't forget to check it. Now if I replace x with 1, this will be 1 minus 2, negative 1. 3 to the negative 1 is 1/3. I wrote that over here. That is a true statement. So x equals 1 works. Wonderful. Alright, next question. Now this involves the base e. And again, you got to recall some things over here. Remember e, when you see e in most mathematics texts, e is a number. It's like pi. Remember e is 2.71828 and so on. Right? It's about 2.7. This number e, this natural base. And something else we're going to have to remember here too is the product property for exponents. If I multiply, if I take b to the m and multiply by b to the n, right, you multiply two expressions with the same base, you keep that base b and add the powers. M plus n would be the new power, the new exponent. Alright, so if you recall this stuff, that'll help with this problem. Because right now it's not the way I want. Remember, I want a single base to a power on both sides. I want this. Right, I want this. Just a single base b to the mth on one side equals the same base, but a single base to a power on the other. Right, so that's not happening here. Right? You see the left side? We got these two bases. I want a single base. Now they're both the same base, which makes it easy to put together, right, using the product property. And that's exactly what I'm going to do before I can apply the 1-to-1 property. All right, so e to the 2x times e to the 3 is e to the 2x plus 3. Right, like that. Now I have a single base to a power on the left equals us, and there's already a single base to a power on the right, e to the ninth. And now I have what I want in order to be able to apply the one-to-one property. Right, the only way two expressions with the same base are going to be equal is if their exponents are equal. Right, so once again, I'm applying this one-to-one property and saying that 2x plus 3 must be equal to 9. Right? And then subtracting 3 would give me 6 divided by 2. X must be equal to 3 then. And let's check it, right? If I plug in 3, 2 times 3 is 6. You have e to the 6th times e to the 3rd would be equal to e to the 9th. Well, that would be true because of the product property, right? E to the 6th times e to the 3rd would be e to the 6 plus 3, would be e to the 9th. This is making this statement true. Again, you can use a calculator if you wish. Most calculators will have the number e, a symbol for e on it. Okay, great. And I've got just one more of these where another property of exponents is going to be needed. And it's all involving base e again. So on the left side we have e to the x squared power divided by e to the 3rd. Notice it's not a single base to a power, it's two bases. I want to make this into a single base to a power before I can apply the one-to-one property. Equals, and then over here it's, it is a single base to a power, e to the 2x power. Alright, so here we need to remember this property, right, the quotient property for exponential expressions. B to the mth divided by b to the nth. Right, when you divide two expressions with the same base, you can keep that base, right, base b, and subtract the powers, right? It's the numerator exponent minus the denominator exponent, bm minus n. Right, so again, hopefully you recall this, all these properties of exponents, because that's going to be needed on the left side here to transform it into an expression with a single base. E to the x squared power divided by e to the 3rd power would be e to the x squared minus 3 power, right? Numerator exponent minus denominator exponent. So now I have what I want, a single base to a power on the left, and I already have a single base to a power on the right. And now I can apply that one-to-one property. Right, the only way two expressions with the same base are equal is if their exponents are equal. So x squared minus 3 must be equal to 2x. All right, and this is another quadratic equation. Let me subtract 2x, x squared minus 2x minus 3 equals 0. And you can use the quadratic formula, try solving with complete the square method, but this is a nice factorable quadratic, right? This factors to x minus 3 times x plus 1. And I apply the zero product property. We can state the solutions pretty quick. X equals positive 3 or negative 1. But don't forget to check these. Let's see. I'll do it off to the side here. If x were 3, on the left side we'd have e to the 9th, right? E to the 3 squared power, e to the 9th, 3 squared is 9, divided by e to the 3rd would be equal to e to the 2 times 3, e to the 6th. And this is true, right? Applying the quotient property, right? This would be equal to e to the 9 minus 3, right? E to the 6 equals e to the 6th. So x equals 3 works. And then when x is negative 1, we'd have e to the first, right? Because negative 1 squared is positive 1. So it's just e to the first, or e, divided by e cubed, equals, and then when x is negative 1, we have 2 times negative 1 is the power on the right side, that's negative 2. And this works too, right? If you apply the quotient property. It'd be e, this left side would be e to the 1 minus 3. 1 minus 3 is negative 2. You'd have e to the negative 2 equals e to the negative 2. That is a true statement. So 2 solutions for this last equation. Positive 3 and negative 1. Wonderful. Alright, and that's it for this particular video. Alright, this set of exercises. Notice in every single one of these, I was doing the same stuff, using properties of exponents to try to get down to the same base to a power on both sides. And then use the one-to-one property of exponentials to set the powers equal to each other, solve, and check. Now, please understand that not every exponential equation is going to be like this, where you can easily write both sides as the same base to a power. Alright, but we'll tackle exponential equations that are probably a little more difficult to do that with in a future video, in future exercises. Alright, so I'm hoping that watching me go through these 7 questions here helps you in some way when you're asked to solve an exponential equation, where both sides can be written with the same base pretty easily. And thank you very much for watching.